Now a bit of theory. So this also we have handled, but slightly with a different perspective we will handle it. I hope all of you can read this. Acceleration relations by analytical method. That is, we have related velocities using all the three methods. We have related the velocity at different points. That is, we are able to relate this Vc with omega and Va. If you take some arbitrary point here, Va bar also we are able to relate with other quantities. Yes. Now the next thing is we will handle the acceleration part. Right? We have also handled that acceleration part while we discussed a rod and things like that. Okay. So the point of contact P does not slide on the surface. Therefore, the component of acceleration parallel to the surface must be 0. That means, I think you can see here, APX is equal to 0. That means there is no component of acceleration along this path. Okay? That is, this particle will not have acceleration here because this point P is momentarily at rest, and the most important thing is this point is at rest. Even though there is friction acting on that, I think we have discussed about that friction, static friction acting. That vector friction that is acting there, it is just that moment for that moment that vector is there, and that friction vector is not going to displace. So there is no motion of that, and it cannot move. That's the basic thing. So therefore there is no question of velocity also of point P, and there is no question of acceleration also of point P. I suppose you got that.
Yes, sir.
Yes, sir.
See, this case is important because unlike the fact that you throw a stone up at the highest point, the velocity is 0, momentarily 0. But acceleration is not 0. Okay, because the gravitational force is acting on that. So here also you see the frictional force at that point is just momentary, and therefore for all practical purpose, rolling without slipping, the frictional force is only used to grip, to take support. It's not doing anything other than that. Provided what? It is rolling without slipping. Okay, and the velocity at the center will be equal to omega r, where r is the radius.
Yes, yes.
Vc is equal to omega r. That condition also must be satisfied, because yesterday we have seen, supposing I have a rolling disk of some omega, disk that is rotating with omega, and then I drop it on the surface. Then what happens? So one of you very nicely said that the things will be in transition till this condition is attached. Which condition? Vc is equal to omega. Till that condition is attached, arrived, there will be changes in Vc and also changes in omega till it reaches. Okay. So, and remember, when you are dealing with all the velocities and all, and we are dealing with this frame xy, so start getting used to this. You should talk now the x component and the y component independently. Okay, so we will not miss out on any aspects. So the acceleration parallel to the surface is 0. However, it has an acceleration component towards the center. Let's not forget it, because this point is a part of the circle which is in motion. See, relative to the ground at this point it is not moving, but relative to this point it is moving. Therefore, there will be centripetal acceleration. Okay, omega square r. The center always moves parallel to the horizontal surface and does not change the direction of the velocity. Therefore, its acceleration can only be parallel to the surface.
Yes, sir.
Okay, if at all there is translatory acceleration, that acceleration will only be parallel. Whereas the acceleration of this will be along this point. The acceleration at this point and the acceleration at this point will be parallel. Got it?
Yes.
So you see, by visual inspection, we can arrive at all these things. Therefore, its acceleration can only be parallel to circle. Omega is not equal to 0 while rolling. That is important here. Of course, even though this point is at rest, omega is still present. Relation between acceleration between the acceleration vector of the center and point P of contact can be obtained with the help of the relation of relative motion put together. That is AC. As we know now, we take these 2 points here, point C and point P here, and we write this equation. AC bar is equal to AP bar plus alpha into PC bar minus omega square PC bar. I suppose all of us, we have derived this equation. So accordingly, we will write this equation here. AC bar, that is here, it will be AC I cap only, because J cap will not be there. And AP by J cap, only J cap will be there. And here, of course, you are writing alpha K cap cross R J cap.
Yes, sir.
R J cap. Because they are writing PC bar here, P to C. Okay. So R J cap and omega square R J cap. Then we do all we open the bracket and do all this. We are getting here so and so, equating the coefficients of x and y on both sides. Okay. So we get the relation which we have already seen. That is I cap here means AC I cap is alpha R I.
Yes.
Okay. So we are getting that the idea is now to get the acceleration vector at C. So the acceleration vector at C is simply going to be alpha R I cap. Obviously, because with respect to this, this point is rotating. With respect to this is rotating, and this is the tangential component. Tangential component will be alpha R I cap. These two doesn't matter.
Yes, sir.
Okay, so that's it. We found out. It's slightly involved, so be careful, because V handling the velocity is separate, handling the accelerations are separate. So this is by acceleration relations by analytical method. I think I did it twice here. Okay, sorry. Anyways, the same thing here. So AC bar is equal to alpha Ri and AP is equal to acceleration of this omega square R J.
Yes.
Okay, that is it's towards the center. See, J cap vector is taken from P to C. Right? And therefore, equation 20 is used for the condition of rolling reverse. Okay, now in the figure given acceleration vectors, the point of contact, center and top of the point. Now we will see how these assets can be using the relative motion equation. Anyway, it should not be difficult. So here, after having done this analysis, so we see here that the acceleration vector at the center is going to be alpha R, and AAY. So this one. So the component of acceleration towards the center will be omega square R.
Yes,
can you see this line here?
Yes, sir.
And the horizontal component of the tangential component will be from with respect to this point, it is going to be alpha into 2R.
Yes, sir. Yes, sir.
No, aram se, just coolly handle this. Coolly handle this. Is this correct? Hello?
Yes.
Now, don't you have the confusion here? Because here, omega square, this point to this, we are seeing it where? AAY. Are we seeing it from this point? We are taking this as the center and handling this?
It's a downmost point, isn't it?
Then
Center
of mass. Then
Yes.
why did you get 2 alpha here?
Acceleration of CM plus acceleration due to rotation.
Yes, sir. Yes, sir.
Yes, sir.
Clear?
Yes, sir.
Okay, because to this actually it will be alpha into r. With
Yes, sir.
respect to center, it is going to be alpha into r. But then to this you should also add this
Yes, sir.
alpha r. Therefore, it will become 2 alpha r. Right? So the two vectors are here, and the resultant vector is this. So therefore, it's very interesting. The acceleration of the center, if it is alpha r, for a disk which is rolling without slipping, and the acceleration of point A is this. See, in the previous cases, if the velocity vector is vc here, with respect to this, vc is equal to omega r. With respect to this va is 2 omega.
Yes, sir.
And both these 2 omega r is I cap, and omega r is also I cap. So there is no vertical component. But as far as acceleration is concerned, you will have a vertical component, while this still remains 2 alpha r. So this will become the resultant.
Yes, sir.
Yes.
Okay. So to be fair enough, so AAX is equal to 2 alpha r I cap, and this is if you are taking this, see, if you have already taken this as J cap, so this will be minus J. Okay, this is it. Aram se, these are not difficult things, but you have to be cool and calm. Then you will definitely see all this thing. In hurry bari, you miss out. The best technique to handle this is you look at x component separately and y component separately. Acceleration. So this we did it by what method? This is what method? This is analytical method. So using this equation, if you are derived it is analytical. And superposition method, well, we will get these vectors separate, and then simply we keep on adding it. And these diagrams are beautiful. So you can see here that the first diagram, they are showing A bar everywhere. So this is the translation acceleration. And, yes. And the next vector you are seeing is omega square r. This is the acceleration due to rotation. And then this is going to be combined effect of all this. Beautiful diagram.
Yes, sir.
Okay, by superposition you can get it. So diagrammatically only it can be. Right, friends?
Yes, sir.
Yes. Yes. Yes.
By Icr method. Okay, right. So by Icr method again, AC bar. So here we have chosen some arbitrary point here P, right? So acceleration of the center with respect to this is alpha r as and then acceleration of top point A is so and so. So already we have derived these two equations. Okay, already we have derived these two equations by taking this as the ICR. Now we are doing this for the point B. No, we got the first two equations. This and this already we have used this, and for that we had taken this as the center reference, and we have used this. Now the thing here is, I'm just telling that because you should not get confused. Already we have used what is it like. Now we are dealing with an arbitrary point B here.
Yes.
They are specifically for these 2 points. And for B again, you will use the same equation here. Only thing is this PB bar, as we have done earlier, you will split it into PC bar and CB bar.
Yes.
Okay?
Yes.
Right?
Yes, sir.
Right? EP bar, PB bar plus alpha PB bar minus omega square PB bar. So, yeah, please follow this. If you want to write down, you can write down. I can give you some time. Write down means you understand this, and if it is not given in your module or something like that, you can write down. If it is already given, then don't have to write down. Is it given in your modules?
Mhm.
Don't know. But you have solved so many sums and all using modules.
Theory.
Theory ಒಂದು 2 ಪೇಜ್ ಇರ್ತೈತಲ್ಲ ಸ್ಟಾರ್ಟಿಂಗ್ ನೋಡಂಗಿಲ್ಲ ಹಾ ಇದು ಕೊಟ್ಟಾರಲ್ಪ ನಿಮ್ಮ ಥಿಯರಿ ಬುಕ್ ಒಳಗ ಚೆಕಿಂಗ್
Sir, there is only ICS. Yes.
Yes, sir. I said.
Nothing about this.
No, if they have used ICR, then all these things must be given there, no?
Analytical.
No, sir.
Not given. Okay, fine. You want to take down?
Okay, sir. Okay.
Take it. See, take down my what you know. You have seen, you understood, you don't see the board and write. You write on your own and then check it with the board. See, that is what I want. Then you are going to learn something, not simply copying it down. Once you have seen, you understand, now don't see the board. After you have completed writing everything, then see the board. That is useful. Okay, not simply B, P, seeing that and writing, no use. See, here PB bar is split as PC bar plus CB bar. Okay, and PC bar is, you know, it is J cap. Okay, it is J cap. That is PC J cap. Okay, and this one you are going to split it into CB cos theta minus I cap and CB sin theta. Okay, minus J cap. Sorry, plus J cap. You are taking this as plus J cap. Then you will separate the terms ing. Sorry, here it should be J cap. No, I have something in my hand.
Sir, then minus omega square PB.
Sir, you open that PB bar and see whether you are getting that equation. Yes, anybody open this PB bar and saw? Hello?
Yes, sir.
You are able to get this only?
No, sir, I just.
Just a minute. A is 2 alpha r omega square r j cap. Okay, so here you see this format 2 alpha r I cap minus omega square r j cap, right? So if you make theta is equal to 90 here, if you make theta is equal to 90 here, okay, then this is sin theta is 1. Okay, sin theta is 1. Then this r becomes capital R. So this becomes 2 alpha r, right?
Yes, sir.
And omega square I cap. The same equation.
Yes, sir.
Hello?
Yes,
It
sir.
may or may not become R.
Huh?
It may or may not become R.
Wait. May or may not become R. Okay, fine.
R plus
Supposing I take to A point and I told you if you take it to A point. So this R becomes capital R. Okay? Now similarly, if you are taken it to this point, then what about the jth component? So cos theta is 0. And this R is now capital R. So this becomes simply omega minus omega square R j cap.
Yes, sir.
Correct?
There is extra.
Wait. Are you getting this from this equation? Right? Or minus omega square R j cap you are
There
getting.
is extra omega square.
There is one extra plus omega square.
Yes,
Yes,
sir.
sir. That equation. And the ith component. Yes.
In the ith component, you are getting an
Extra
extra.
alpha. Omega.
बिल्कुल है,
Sir, omega square into what, sir?
बिल्कुल है, ये ना गड़बड़ है.
Yes, sir, limit not, sir.
See,
If we take only omega square, it
See.
will be dimensionally incorrect. Yes, sir.
Omega square term shouldn't be included.
so the I cap term omega square should not be there. Correct? No. Hello. The second term is correct. The second term is correct. Right?
Sir, can you please scroll down?
I'll slow down. See, you see this? No. The second term is correct. The first term, 1 omega square is coming extra.
That's what extra is.
Okay, so it should not come.
So it should come sir, but with r minus omega square.
So but there is no omega square in I.
See, if you put theta is equal to 90, man. Arun, if you put theta is equal to 90 and r is equal to capital R. Okay, so I should get only 2r alpha I cap. Correct? No?
Yes sir.
And this cos 90 is 0. So I should get here minus omega square r.
Yes sir. Yes sir.
Okay, so that is precisely. So this omega square term that is coming here is an extra term.
So
Yes, sir.
it should be alpha sin theta sir, in second term. Second and j cap term.
Alpha r.
sin theta.
Why sin theta?
And sir, the inner one should be cos theta sir. For in the I cap term sir. Plus r cos theta sir.
R cos theta. Hello friends, did you check it out?
Yes sir, I split it up. Yes, sir.
Okay,
So,
fine.
sir, for that small r sir, there in figure sir. In the figure, small r.
You
minus-
say you are telling you say you should get cos theta here.
Yes sir.
So if you put cos theta here, gentlemen,
Minus-
listen.
Yes sir.
If you put cos theta here, gentlemen, and if I take this point B to this point, what will I get? Cos theta is 0.
Okay. But
Then you will
alpha-
get alpha r. I should get alpha 2r, man.
Sir, but
Alpha
Sir,
2r.
sin theta is correct.
See, you see,
Okay.
I'm telling you, no, you are see here, look here.
yes sir.
See, this is how you should verify whether. See, I also had doubt in that equation. So for me, I want to quickly verify whether it is right. So what did I do? I took that point B to this point, and when I took this point to B, this point here, I should get this term. Okay, so that's what I am looking for. Okay, so will I get that term? So here, you see, so if I put sin theta is equal to 90 and the small r is equal to capital R, then this will suffice. Okay, I'll get this into I cap. This omega square is extra term. And here if I put 90, this goes off. Then I am getting here minus omega square r, j cap. So this correct. So this omega square is the culprit. Right? And dimensionally, if you see here, alpha omega square is what? Radian square divided by secant square. Correct? Hello?
Yes sir.
And alpha is a radians per secant square.
Yes.
So, dimensionally also it is not okay here.
Sir, 1 minute.
Anyway, see, listen, you please verify this, no? Hello?
Yes. Yes, sir.
Please verify this, and the first thing we will do tomorrow is we will verify this.
Okay.
Yes, sir.
Yes? Because that is why I stopped here and asked you to have a look at it, because I too was feeling something is not right here. Okay? Please do that. Shall I proceed, students?
Yes.
Hello?
Yes sir.
Yes, sir. Yes.